the class here we'll start with high pass filter, the design of high pass filter. We had seen first order high pass filter. Now we'll see the design of high pass filter. It is same as low pass filter where we take the cutoff frequency for 1 kilohertz. To design, we had assumed the capacitor value as 0.01 microfarad. So by assuming the capacitor value, you have to find out the resistor value by using the formula R is equal to 1 by 2 pi F into C. Substitute F and C, you will get the value of R. And since the gain is AF, gain is 2, so just take the values, that is the feedback resistors R1 and RF as 10 kilo ohm to get the gain as 2. So this is how to design a high pass filter. Next, if you want to plot the frequency response, just go with the formula V0 by Vin is equal to AF into F by FL divided by root of 1 plus F by FL whole square. Substitute the values, you know AF, you know FL, and take F as from 100 Hertz to nearly 1 kilohertz or 100 kilohertz. You'll get the gain magnitude, find out the log of it and multiply it with 20 to get the value in decibels. Next, this is the plotting the first order high pass filter, where first we'll have a stop band, then we'll have a pass band. This is the frequency response of first order. Next, we'll move on to second order high pass filter, which is same as second order low pass filter. Only the frequency determining resistors and capacitors will be changed. That is the second order. In second order, so in high pass we have seen that the input will be given for capacitor. So one capacitor and one resistor will be extra here. So we have C2, C3, R2, R3 for second order high pass filter, and the response will be nearly equal to the ideal characteristic. The roll off will be for 40 decibels per decade. As the order increases, the roll off from in the stop band will be very nearing to the ideal characteristic. And here the resistor R2 is fed back to the output, and we have R1 and RF as the feedback resistors. So in second order, only the frequency determining resistors and capacitors are increased. Okay, more than in first order will have one resistor and one capacitor. In second order we'll have one more resistor and capacitor. Both the circuit and frequency response is shown, and we can put the voltage gain magnitude by using the formula. The design of second order high pass is same as second order low pass. The formula is FL is equal to 1 by 2 pi root of R2, R3, C2, C3. We had taken for simplification, we had assumed that R2 should be equal to R3 and C2 is equal to C3, and assumed the value of capacitor as 0.0041 microfarad. Just by substituting all the values, we'll get the FL as 1 kilohertz. Okay, and the frequency response, it is taken as AF divided by root of 1 plus FL by F to the power 4. Here the term, that is F by FL in the numerator, is removed by cross multiplying. So at the denominator we'll get FL by F2. Okay, that is the term that is used. And now we'll see what are these higher order filters. First we saw first order and second order. Next we'll see what is this third order and fourth order and how to design them. So one more important thing is, as the order increases, the stop band response of the filter, okay, the stop band response of the filter will approach a ideal characteristic. That is important. So we'll see how to design a third order low pass filter. It can be designed by combining first order low pass and second order low pass. So when we combine these two filters, or when we cascade these two filters, then a third order low pass filter will be designed. Cascading means the output from the amplifier A1 is given as input to the second order low pass filter, that is to the resistor R here. Okay, so the input in a low pass filter, the input will be given for resistor, and here the output from the amplifier A1 is given to the amplifier A2. This is third order. If you want fourth order, then two second order filters are cascaded. Two second order low pass filters are cascaded, which second order means we have two resistors and two capacitors. Okay, they are cascaded and we'll get the fourth order low pass filter. Same thing can be followed for high pass filter also. If you take a first order high pass and second order high pass, we can form a third order high pass filter. As the order increases, as we have seen in the frequency response, the stop band characteristic will be very near to the ideal characteristic. We had seen that for first order the roll off is 20 decibels, for second order it is 40, for third order it is 60, and for fourth order it is 80 decibels per decade, the roll off. Okay, so this is the frequency response of high third order and fourth order filters. Next we'll see about what is this band pass filters. So band pass filter means a band of frequencies are allowed, that is the band of frequencies between FH and FL are allowed to pass, and the frequencies which are less than FL and which are greater than FH is not allowed. In band pass filters we have two types, one is a wide band pass and one more is narrow band pass. So we use a figure of merit or a quality factor Q to differentiate between wide band pass and narrow. If Q is less than 10, we call it as a wide band pass, and if Q is greater than 10, we take it for a narrow band pass filter. And this quality factor Q is got by the formula FC divided by bandwidth, that is FC divided by FH minus FL. What is this FC? FC is the center frequency and it is given by the formula root FH and FL. FH is the high cutoff frequency and FL is the low cutoff frequency. Okay, that is shown here. So first we'll see how to design this wide band pass filter. Wide band pass filter is got by cascading. What will cascade? One is high pass and low pass filters. So we will get both the first order filters here. First one is the high pass filter and second one is the low pass filter. In high pass filter the input is given for the capacitor, and in low pass filter the output from the amplifier A1 is given to the resistor R. Since we had seen the response of band pass filter where the gain increases, it becomes constant and then decreases. Okay, this characteristic can be obtained by cascading high pass filter and low pass filter, both of first order. So the response is shown here, and the band pass filter has two stop bands and one pass band. That is the gain versus frequency response is shown here. And here the input is for high pass it is given for capacitor, and the output from the amplifier A1 is given for the resistor R. This is a wide band pass and it has two op amps. We have seen it has two op amps and the frequency response is very wide. This in narrow band pass filter, the response is very narrow and they design it with only one op amp. And one more important thing is here the op amp is used in the inverting mode. By inverting mode means the input is given for the inverting terminal, and nearly we have two feedbacks for the narrow band pass filter. We first will see the circuit. We have one resistor R3 which is taken as feedback, and one capacitor C2 also is taken as feedback, and we have only one op amp, and here the response is very narrow. The response is shown here and it is very narrow when compared to the wide band pass, and we have three frequencies FL, FC and FH. FC is the center frequency, FL and FH are the lower and higher frequencies. So it is gain versus frequency, and input is given for the inverting terminal. So it is in the inverting mode and the non-inverting terminal is grounded, and we have two feedbacks. So this is the circuit for narrow band pass filter, and we have to find out the values R1, R2, R3. These are the three values that need to be found out. The three values are found by using the formula R1, R2, R3, that is Q divided by 2 pi FC C into AF, and one more the formula is for R2, and the R3 is Q divided by pi FC into C. And the gain is AF is equal to R3 divided by 2R1. See, this is the gain at center frequency FC. It is R3 divided by 2R1. That is R3 divided by 2R1. and by assuming the capacitor value C as 0.01 microfarad, and they have given quality factor as 3, and frequency is 1 kilohertz, we can find out the values for R1, R2 and R3. Okay, so it is 4.7 kilo ohm is the standard value, and R2 is 6.2 kilo ohm, and R3 is 95.5 is nearly taken as 100 kilo ohm. All these three resistor values, that is R1, R2, R3 and C1, C2 as 0.01 microfarad, can be substituted in the narrow band pass filter to get or to design a narrow band pass. Okay, so this is all about the first order low pass and high pass filters, second order low pass and high pass filter, and band pass filters. In band pass filters we have two types. One is wide band pass and narrow band pass, and higher order filters also can be designed by using first order and second order filters. As the order increases, the response of the stop band will be very near to the ideal characteristics. In next class we'll move on to the next one is we'll move on to band reject filters and all pass filters. And one more important thing is, in a low pass filter the input is given for the resistor, and in high pass filter the input is given for the capacitor. As we increase these frequency determining components, that is resistors and capacitors, the order of the filters can be increased, and always the design of the filters will depend by assuming the capacitor value. We have to assume one of the capacitor values and find out the resistor values to start the design of the filters, and see whether the filter is in the inverting or non-inverting mode. Most of the filters are kept in non-inverting mode, that is the input is given for the non-inverting terminal and the gain is 1 plus RF by R1. Only for one filter, that is narrow band pass filter, the input is given in the inverting mode and it has two feedbacks. Okay, that is the difference here, and the difference between narrow and band pass is got by using the quality factor Q. Thank you.